Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all in today's session. Well, to access the notebook for today's session, you can access the course page on my personal website arif.me. You can click the appropriate link under the lecture resource column to view it in NB Viewer and run it online in Binder. The other way is to download the notebook file from the course GitHub account, Arif PUC and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 4.4 of the fourth module for the course titled Tools and Techniques for Data Science. My dear students, this is part 2 of linear algebra for machine learning. And in part 1, we covered the basics of linear algebra in 3 segments. Let me show you that first. Well, in the previous session, in segment 1, we discussed the mathematical and graphical representations of vectors in 2D and 3D space. We learned to compute the magnitude, direction and components of a vector, discussed the addition, dot and cross product of two vectors. We also understood the concepts of unit and basis vectors, their linear combinations, and the span of basis vectors in the entire 2D space. Well, the section number 2 of previous session was about matrices, in which we started with understanding matrix types like row and column vectors, square and symmetric matrices, triangular, diagonal, identity and orthogonal matrices. We discussed different matrix operations like matrix addition, matrix Hadamard product, matrix dot product and so on. We also learned to compute the Frobenius norms, transpose, determinant, inverse, trace, and rank of a matrix. And finally, in the previous section, section 3 was related to solving the system of linear equations. We started from the very basics, from understanding what a linear equation is, having 2, 3, 4, and so on to n variables, and how to plot them graphically. We practically understood the difference between consistent independent, consistent dependent, and inconsistent system of linear equations. We also saw how we can represent a system of linear equations in matrices form, and that is a commonly used technique to solve them. And the technique that we discussed in the previous session was Gaussian elimination. We also discussed Gauss-Jordan elimination, Cramer's rule, and a simple matrix inversion method as well. My dear students, then we practically understood the difference between overdetermined and underdetermined system of linear equations, and discussed the least squares method that is used to solve simple as well as multiple linear regression problems. Well, my dear students, all this was done with lots and lots of Python code examples for a crystal clear understanding of all these concepts. Well, if you have not seen them or are not comfortable with these concepts, I strongly recommend that you should watch that video first and then fall back to this. My dear students, linear algebra is one of the fundamental block of data science. And you cannot think of building a skyscraper without a strong foundation. And without the proper mathematical background, most of the machine and deep learning algorithms will be like a black box to you. And you will not be able to choose the proper hyperparameters and develop a better machine learning model. Solving overdetermined inconsistent system of linear equations was one of the applications of linear algebra in machine learning that we discussed in the last lecture. Similarly, sport vector machine, that is a discriminative supervised machine learning classification algorithm, is also mainly based on the concept of vector spaces and use vector norms to calculate the margins. In deep learning, we often have data sets having thousands of variables, and we need to select important ones out of them. The two linear algebra techniques used for this dimensionality reduction are principal component analysis and singular value decomposition, which inshallah we are going to cover today. Similarly, in the field of digital image processing and computer vision, one cannot think of storing and manipulating images without the use of matrices and tensors. And last but not the least, singular value decomposition is used in implementing the algorithms of latent semantic analysis and topic modeling in the domain of natural language processing. Well, I think that is enough of motivation. Let us move on to the agenda of today's session. Okay. So section 4, matrix as a linear transformation. This deals with linear transformations like scaling, reflection, shear, and rotation. My dear students, if you are comfortable about these basic linear algebra concepts, you can straight away move on to the topic of your choice by clicking the appropriate subtopic in the description box below. However, I strongly recommend that you should go in sequence, since all the topics are interrelated and every next topic requires the knowledge of the previous one. Anyways, section 5 deals with the two famous and most common matrix decomposition techniques, Eigendecomposition and singular value decomposition. I have gone step by step to make these tricky but important concepts easy to understand by solving lots and lots of examples using Python, NumPy, SciPy, and Scikit-learn library. And finally, section 6, I have discussed in detail in this notebook 3 out of many application areas of Eigendecomposition and singular value decomposition. And these are image compression, principal component analysis, and Moore-Penrose Pseudoinverse. Once again, my dear students, if you want to jump into the ocean of machine learning and deep learning, this is the foundation you need in order to build your skyscraper in this domain. So let's start playing. And let me keep sipping this cup of tea because it appears that this will be a long session. Fine. Okay, my dear students, these are the libraries that we need to import. Pay specific attention to this plot helper module that contains code for drawing the vectors and for linear transformation as well. We have used it in the previous session as well. Some of the codes of this notebook are adapted from these GitHub repositories. I am particularly thankful to Dr. Kron for providing such marvelous resources on this subject. Okay. So what do you mean by applying a matrix to a vector? My dear students, in this section, we will practically understand the concept of linear transformations and how they relate to the idea of matrix vector multiplication. In linear algebra, a transformation is a function that takes a vector as input and gives a vector as output. There are a variety of transformations, some of which are quite complex. But in today's session, I will restrict myself to the most basic type of transformations called linear transformations. When one vector space is linearly transformed to another, remember the lines remain lines and the origin remain fixed. Let's see this practically. Well, when we multiply our matrix with a vector, we say that we are applying a matrix to a vector. This actually linearly transform this vector, and the resultant vector may get scaled or rotated or maybe translated. Let's move on to an example. let us apply this 2 by 2 matrix, on these two basis vectors. So this is the matrix 1, -1, 1, 1, and the basis vector along x-axis is I hat having coordinates 1, 0, and the basis vector along y-axis is j hat having coordinate 0, 1. So this is your 2D Cartesian coordinate system before we applied this matrix onto these two vectors. And once we apply this matrix to these two vectors, after transformation, we have the vector somewhat like this. And let me repeat my difference. The columns of for transformation matrix 1, -1 and 1, 1 are the landing spots for the basis vector. This plot underscore linear underscore transformation function is used to visualize what this matrix A will do to these two basis vectors I and j. So this green vector is the basis vector along the x-axis having coordinates 1, 0, and after transformation matrix is applied to this basis vector, this lands at 1, -1. So this 1 and this is -1. So this lands at 1, -1, which is the first column of this matrix. Similarly, this red vector is the basis vector along the y-axis having coordinates 0, 1, and after transformation matrix is applied, this basis vector lands to over here 1, 1, which is the second column of this transformation matrix 1, 1. It seems that both these vectors are rotated clockwise by 45 degrees along with some scaling as well. You can see their size has a bit increased. Moreover, do note that this helper function plot linear transformation has applied the matrix A on the entire grid. Note that all the horizontal and vertical lines of the grid has been rotated as well as scaled. And since parallel lines remain parallel after transformation and the origin is not changed, you can see, so this is a linear transformation. Okay, so let me see another example to make you understand the concept of linear transformation in 2D space. Before I show you more linear transformation examples, let's once again see the algebra that works behind the scene. Suppose you are given a 2 by 2 matrix A and a vector v1, and you want to find out where this linear transformation or this matrix will take this vector. So you simply multiply the matrix A with this vector. So the new coordinates are x2 is equal to a1 x1 plus a2 y1, which is achieved after multiplying these two, this matrix and this vector, and y2 is equal to a3 x1 plus a4 y1. You can always write down in homogeneous coordinates this matrix, but it is perfectly fine if you are doing it in 2D space. So that means this linear transformation, this matrix A has taken this vector containing 2 points x1, y1 to a new vector v2 having coordinates x2, y2. Let us start by applying an identity matrix to this one. So this is an identity matrix, and let me apply this identity matrix to this vector x1, y1. Let me take exact values. Let me take the vector 3, 1, and let me multiply this matrix with this vector, and this is what has been done over here. I think the code is quite simple. We have been going through such like codes in our previous session a lot. This plot vector is going to plot the vector v1, and this plot vector is again going to plot the vector v2. So let me execute this code. After multiplication and before multiplication the vector is same 3 1. So that means this identity matrix once applied on any vector does not make any change to that. So before transformation this is the vector 3 1, and after transformation this is the vector 3 1. So there is no change to it. So this proves that by applying an identity matrix it has no impact on the vector whatsoever. And let me run this as well and apply it on the entire grid. You see there is no change. Remember this time I'm using plot linear transformation function. So it is showing the entire grid. There is no change after we apply this identity matrix onto this entire 2D Cartesian coordinate system. Let me show you a scaling matrix now. Scaling is a process of expanding or maybe compressing the dimensions of an object. Note the matrix that is used for scaling. This Sx is the scaling constant with respect to x direction, and this Sy is the scaling constant with respect to y direction. And if both of these Sx and Sy are same, we say that the scaling transformation is homogeneous. And if any one of them, either Sx or Sy, is greater than 1, we say it is magnification, and if it is less than 1, we say it is compression. And of course a value of 1 will have no effect. Let's see this practically. So this is a scaling matrix, and this is a vector on which I am going to apply this scaling matrix. It appears that once this transformation matrix or scaling matrix will be applied on this vector, it will scale the x coordinate from 3 to 6 and the y coordinate from 1 to 4. And let me execute the code of this cell. And you see before the transformation the vector is 3 1, and after the transformation the vector is 6 4. This might not be visually very apparent, but do note the scale of the Cartesian coordinates. Okay, so let me use now this plot linear transformation helper function and pass it the scaling matrix and see the impact. Great. Observe the green vector along the x-axis has scaled twice its length, while this red vector along the y-axis has scaled 4 times. And other than these two vectors, the same impact can be observed on the entire grid. One more important point I just want to show you practically is that applying the inverse of scaling matrix on the new or transformed vector 6 4 will undo the effect of transformation. So let me this time apply the inverse of A onto this. So let me compute the inverse first. So this is the inverse of that matrix, and over here I am passing it. You see, once we apply it, we have 6 4, and after that we have 3 1, and over here you see 3 1 and 6 4. I hope this is making sense to you all. I have shown it mathematically as well over here. And let me use the plot linear transformation function and apply matrix A on it, and then apply the inverse of matrix A on it. Note that this time I am using a plot linear transformations function, which is used to apply two matrices or two transformation at the same time. So this is before transformation, the grid. After first transformation, after we have applied A, so this I hat is scaled by 2, this J hat is scaled by 4, And let's see, once we apply this inverse of A to this, you can see after the second transformation it has moved back to the same. My dear students, please stop the video, rewind, watch it again, so that you should have very clear understanding of how we can apply a transformation matrix on a vector, and how we can apply multiple transformation matrices on a vector. And the important point is applying a transformation matrix and then applying the inverse of that transformation matrix brings the vector to the same dimensions. Great. Let me move on to reflection now. Well, my dear friends, reflection is actually the mirror image, and it can be about the x-axis, about the y-axis, or maybe about the diagonal. Note the three transformation matrices used for the three types of reflection. Other than the change of sign, it is exactly like the identity matrix. So over here I have a -1 over here. So this transformation matrix will reflect the vector along x-axis. Over here I have a -1 at this location. So this transformation matrix will reflect about y-axis. And when I have a negative sign at both locations, then this transformation or reflection matrix will transform this vector about the diagonal. Let's practically understand this with an example. Okay. So when you apply this transformation matrix on this vector 3, 2, it will be reflected about x-axis. That is, the y coordinate is negated, and the new vector will be 3 minus 2. Let's execute the code of this cell. You see, 3 minus 2. And let's see the visual representation as well. So this is before transformation, the vector 3, 2, and after transformation, it is 3 minus 2. So it is reflected about x-axis. So this is the original vector, and this is the transformed or reflected vector along the x-axis. Okay, let's apply the reflection matrix on the entire grid using this helper function, plot linear transformation. So you see, everything is reflected. Observe the green vector along the x-axis having coordinates 1, 0 is the same, that is no change. However, this red vector 0, 1 has been transformed to 0, minus 1. My dear friends, actually all the grid intersecting points above the x-axis has been moved below the x-axis, but visually you cannot make this out from these two images. So I will not be wrong in saying that the columns of the transformation matrix are the landing spots for the basis vectors once again. And finally, let's see this helper function, plot linear transformations with a S, and pass it two transformation matrices, the matrix A and its inverse, which I am calculating using the INV method of the linear algebra module of NumPy, used many a times in the previous session. Let me execute this code. Great. Note this is before transformation. The two unit vectors shown in green and red along the x and the y axis. After first transformation is applied to the red unit vector is reflected about the x-axis. The green unit vector stays as such. The second transformation over here actually applies the inverse of matrix A on this grid, and everything goes back to normal. And you can observe this from the red vector that is reflected back again about the x-axis. I hope this makes sense to you all. Now let's talk about shear transformation that causes an image to slant. The two types are shear in x direction and shear in y direction. Note the transformation matrix for x here. It is an identity matrix having a scalar value at the top right, and when it is multiplied with the vector, the y coordinate remains same while the x coordinate will be tilted up or down. Similarly, the transformation matrix for y shear has a scalar value in the bottom left position and results in, of course, changing the y coordinate. Let us practically understand this with an example. Excuse me. So this is our transformation matrix that performs an x shear with a value of 3 when applied on this vector 2, 2. And the transformed vector will be, of course, 8, 2. Let me execute this code. You see the transformed vector is 8, 2. I've used again the plot vector function to plot both the vectors before and after the transformation. So before the transformation, the vector is 2, 2. And after the transformation, the vector is 8, 2. Great. My dear students, this will make more sense to you when you apply this x here matrix on the entire grid using this helper function, plot linear transformation. Let me apply this. Great. Note the y coordinates remain same. However, the x coordinates changes. There is no impact on the green vector. It remains 0, 1 over here, 0, 1 over here. However, the red unit vector, that was this 0, 1, this green was 1, 0, which stays at 1, 0. This red was 0, 1, and it has been transformed to 3, 1. Also note that all the vertical grid lines are tilted. All the vertical grid lines, the blue lines, are tilted. So once again, I can say that the columns of the transformation matrix, are 1, 0 and 3, 1. These are the landing spots for the basis vectors. So the basis vectors have been moved to those places. Okay, so let me make some minor changes in the transformation matrix. Instead of this 1, 3, 0, 1, I am making it, what should I make it? Let me make it 3. Okay, so let me put a minus 3 over here. So instead of 1, 3, 0, 1, I am doing it 1 minus 3, 0, 1. Let me execute the code and see. Note that this time the vertical grid lines are tilted in the other direction. Previously they were tilted in this direction. My dear students, do play with this to have a clear understanding. And let me do a y shear now. I can do the y shear by doing 1, 0 over here. Okay, let me do it over here. 1, 0 and 3, 1. So this will be a y shear. Let me execute it. Note that there is no impact on the red vector this time. The vertical lines, all the vertical lines shown in blue are same. However, the horizontal lines are tilted, and so is the green vector as well, which has been transformed to now 1 and 3. So this is what shear is. And finally, let us perform both x and y shear at the same time. Let me do it something like this: 1, 3 and 3, 1. So I'm changing it like this. Let me execute the code. Great. So you see both these vectors, the green vector as well as the red vector, they both are moved, rather all the grid lines, the horizontal as well as the vertical lines are transformed. Please do play, have different values at these places. This is a marvelous function that will visually draw all the transformations before and after, so that you can have a crystal clear understanding of how it works. And of course, once again, we can always apply this plot linear transformations function with an s at the end to apply two transformations. First, I'm applying the transformation A, and then I'm applying the inverse of A. So you see, after I have applied A, I have moved here. After I have applied the inverse of A, I have moved back. Once again, I just hope that this makes sense. Let's move ahead to the rotation matrix now. My dear students, most of the time we use counterclockwise rotation. However, I have shown both the counterclockwise as well as the clockwise rotation matrices over here. And naturally, to apply a counterclockwise rotation matrix to a 2D vector, we multiply them. And the corresponding linear equations are also shown over here. And theta is the angle of rotation. Let us practically understand this with an example by rotating a vector 2, 3 by, let's suppose, a counterclockwise rotation of 90 degree. Over here, note these first two lines. These are creating the vector and the rotation matrix. And then over here we are performing the dot product. Of matrix A with this vector. And finally over here I'm using the plot vector function to plot it. Let me execute the code if this makes sense. So this is the rotation matrix that I have created. Once applied on V1, which is 2, 3, it has transformed the vector V1 to the location -3, 2. Let's see this visually. So this was the vector 2, 3 before transformation. And after transformation, it has moved to -3, 2. And you see that it has been rotated by 90 degree in this direction, that is in the counterclockwise direction. Great. Let me now apply the helper function plot linear transformation on this same rotation matrix. Let's check out. And you see that after the transformation, this basis vector green has moved on to this place, and this basis vector red, that is j hat, has moved on to this location. That is, both the vectors have rotated counterclockwise by an angle of 90 degrees. Please do note that the basis vector I along the x-axis was having coordinates 1, 0 before transformation is mapped to 0, 1 after transformation. That is, the landing spots of both these basis vectors are once again the columns of this transformation matrix. That is 0, 1 and -1, 0. So this is 0, this is 1, and this is -1 and this is 0. Roughly, you can say that. Okay, for completeness, let's do another example and rotate this 2, 3, this vector 2, 3 by an angle of 45 degree. And this time again in counterclockwise direction. The code is same. Let me execute it. So you see now this time it has moved by an angle of 45 degree. So this is the rotation matrix that when applied on this vector 2, 3 transforms the vector to -0.7 and 3.5, And this is how it graphically looks like. This vector v1 was 2, 3, and this vector v2 was minus 0.7, and over here it is roughly 3.5. I hope this makes sense. And over here, let me use the helper function, plot linear transformations with a s at the end to apply the rotation matrix and then its inverse to the output. So let me run it. You see, after the first transformation, both the unit vectors are rotated counterclockwise by 45 degree. Rather, you can see that all the grid lines are rotated by 45 degree counterclockwise. And once we apply this inverse of this matrix on this, everything goes back to square one. Great. Let's move on to translation. Well, my dear students, translation does not fall under linear transformation since after the translation the origin changes, and the basic requirement for a linear transformation is that the origin remains at the same place. However, since it is also a very basic transformation, so I have shown its matrix over here, which can be written in these two forms, homogeneous as well. Okay, so we have already seen that we can apply multiple transformations simultaneously, one after another. So over here, this example code actually do a scaling and then rotation. So we are doing a scaling first, and then we are applying a rotation, scaling and then rotation. So the scaling matrix is 2004, and this is the rotation matrix. Let me execute it. So this is the scaling matrix and this is the rotation matrix. So before the transformation, the 2D Cartesian coordinate is shown over here, and once we have applied the scaling, that is 2004, this is the new grid. Note that this green vector I had unit vector along the x-axis 1 0 lands on 2 0, and this unit vector 0 1 red vector, this lands onto the second column, that is 0 4 0 4. So this is once again proof that the unit vectors are transformed to the columns of the transformation matrix. So after the scaling, we have applied the rotation. So this is the rotation matrix. Once the rotation matrix is applied over here, you can see that this is the visual representation of the vector after both these scaling as well as the rotation matrices are applied. My dear friends, once again, it is important to note that the order of transformation is important. Over here in this code, we have first applied the scaling and we have got this, and then on this matrix I have applied rotation and I have got this. Let me prove this with an example in which I have applied the rotation first and then the scaling. Let me execute this code. So this is the input matrix. We have applied rotation and then we have applied the scaling. You can observe that over here we have the final output something like this, and over here we have something like this. So the red vector is having minus 4 0, and over here the red vector is minus 2 0. Hope this makes sense. Anyway, let us move ahead, and let me quickly touch upon the transformation in 3D space as well. My dear students, if you have properly grasped the 2D transformation, I think you can easily extend that knowledge to 3D as well, which is shown over here, just the matrices. The transformation matrix for 3D space can be represented as a 3 by 3 matrix like this, or as a 4 by 4 matrix in homogeneous coordinates. The scaling, translation, and counterclockwise rotation about z-axis, x-axis and y-axis are shown over here. Interested students should also explore these isometric similarity a fine and projective transformation. Well, these details are normally touched upon in the subjects of digital image processing and computer vision. And I think enough of the transformation that we need for this course of linear algebra. Let me move on to the next part, and that is uh, decomposition, Eigendecomposition and singular value decomposition. Okay, my dear students, I think I have set the stage right for you all to move on to another very important concept in linear algebra, and that is matrix decomposition. My dear students, the way we can write an integer as the product of its factors, similarly we can write a matrix as a product of its component matrices. So formally speaking, matrix decomposition is the process of reducing a matrix to its constituent parts in order to make certain subsequent matrix calculations simpler. Well, there is a whole list of techniques that exist in literature which can be used to decompose a matrix into its submatrices like LU, LR, QR, and Cholesky decomposition. But today we will restrict ourselves to the two most famous and most commonly used matrix decomposition techniques in data science and machine learning, and these are eigendecomposition and singular value decomposition. And before I describe eigendecomposition, let me put the stage right by making you understand what eigenvalues and eigenvectors are and what they have to do with eigendecomposition. Okay, so first of all, the word eigen. The word eigen is a German word which means characteristics. Well, eigenvectors of a transformation matrix A are the vectors that does not change their orientation but just scales by a factor of its corresponding eigenvalues. Mathematically, it is written as AV is equal to lambda V. So if A is a transformation matrix, that when applied on a vector V, you again get a vector V which is just scaled by a scalar value lambda. This is what this expression says. Once again, let me say that if this V is an eigenvector of transformation matrix A, then multiplying the matrix A with this vector V is the same as multiplying the vector V with the scalar value lambda. So over here, if this equation satisfies, V is said to be the eigenvector of matrix A, while lambda is called the corresponding eigenvalue. Don't worry if this doesn't make much sense to you. We will soon see it practically by taking different examples. Right now, let me give you an abstract view. Okay, consider this image of Mona Lisa on the left with a red and a blue vector, both having a length or magnitude of 5 units. And suppose we apply a flipping matrix on this image, and the resultant matrix or image is shown on the right. You see the image is flipped. Over here, this water channel is over here on the left, and right now over here it is flipped. It appears that the red vector is multiplied by a scalar value of 1, no change, while this blue vector is multiplied by a scalar value of -1. So it has been in this direction. So both these red and blue vectors are eigenvectors of this flipping matrix with corresponding eigenvalues of 1 and -1 respectively. Okay, let me show you another example. Okay, once again consider this image of Mona Lisa on the left with a red and a blue vector. And suppose we apply a shearing matrix on this left image, and the resultant image is as shown over the right. Note the direction of the red vector is changed. However, the blue vector maintains its direction. So this blue vector is the eigenvector for the shearing matrix. with an eigenvalue of 1 as the magnitude remains same. Let me show you another example. And suppose this time we have applied our flipping plus shearing matrix on this left image, and the resultant image is shown on the right. Since the red vector is knocked off its span, so it is not an eigenvector for this transformation matrix. However, this blue vector is an eigenvector because it has not been knocked off, and this eigenvector has an eigenvalue of -1 because it has just reversed the direction. Okay, so my dear students, let me reiterate the formal definition of eigenvectors and eigenvalues. Eigenvector of a transformation matrix A is the vector or are the vectors that does not change their orientation but just scales by a factor of its corresponding eigenvalue. Consider this matrix A 1, 3, 2, -4. The two eigenvectors for this scale matrix A of size 2 by 2 are 2, 1 and -1, 3, with corresponding eigenvalues of 2 and -5 respectively. And of course, note that we can always normalize an eigenvector by dividing its element by the L2 norm as shown over here. Now a $100 question is, given a transformation matrix A, how can we determine or calculate its eigenvectors and their corresponding eigenvalues? So if this is eigenvector, how should I come to know that this is the transformation matrix A? How can I come to know that this is the eigenvector? So let's see this mathematically first. So over here I have written this AV is equal to lambda V, this equation in the matrix form, where A is a n by n scale matrix. This V1 is a column vector of length n, and this lambda is some scalar value. As per the definition, when we apply this matrix A on this specific vector V1, its direction remains the same or is shifted to 180 degree, and its magnitude may be scaled or expanded or squished by this value lambda. That is to say, this matrix equation AV is equal to lambda V holds true. Then we say that the vector V is an eigenvector of transformation matrix A with the corresponding value lambda. My dear students, instead of multiplying this scalar value lambda with this vector V on the right hand side of this matrix equation over here, we can replace this lambda with this diagonal matrix. So instead of this lambda, I have just replaced it with this diagonal matrix. And then over here, what I have done is I have just replaced this with an identity matrix. So this is an identity matrix and this is a lambda. This is the same again. So if I write it down, I can write it as A into vector V is equal to lambda into the identity matrix I multiplied by the vector V. And if I can move this portion onto the left, I can say that A minus lambda I multiplied by this vector V is equal to 0, which means that A minus lambda I is a matrix that has a non-zero vector V in its null space. So we can say that this A minus lambda I is non-invertible, that is, its determinant is 0. So this is the equation which is of our interest right now, which we will use to find out the eigenvalues and eigenvectors. So determinant of a minus lambda I will be equal to 0. So this is one equation, and the other equation is a minus lambda I into v is equal to 0. Keep these two equations in your mind, and let me try to solve this example step by step using a paper and pencil. Okay, consider this 2 by 2 matrix A, 1, 3, 2, minus 4. I wish I have a whiteboard so that I can draw it step by step, but bear with me. I have tried my best to write down all the contents that I could have written on the whiteboard on this Jupyter notebook. So anyway, let's suppose that this is a 2 by 2 matrix, and I want to calculate the eigenvalues and eigenvectors corresponding to this matrix. So step 1 is we need to calculate the eigenvalues. And to calculate the eigenvalues, this is the equation which I am going to use. Determinant of a minus lambda I is equal to 0. So first of all, I need to compute the matrix a minus lambda I. So this is a, this is minus lambda I, and this is the final equation, a minus lambda I. Now I need to calculate the determinant of this matrix. So the determinant of this matrix gives me this equation over here, you see. And these are the two values of lambda, 2 and minus 5. I hope this math is very simple. You can understand it. A point to ponder is that in an n by n matrix, over here we have a 2 by 2 matrix. If there is an n by n matrix, it can have a minimum of 1 and a maximum of n eigenvalues, and which is when all the columns of the matrix are linearly independent. So this is a 2 by 2 matrix, and it is having 2 eigenvalues. And if there is a 3 by 3 matrix, it can have a maximum of 3 eigenvalues. And if the two columns are not independent, they are dependent, the number of eigenvalues can be less than the number of columns. Okay, so now we have the two eigenvalues of this matrix A, and we need to compute the eigenvectors. And for that, what I'm going to do is I'm going to substitute the values inside this equation, a minus lambda I into v is equal to 0. So first of all, I'm just substituting the value 2 into this equation, and once I substitute that value, it falls back to this equation, 3v1 minus 6v2 is equal to 0. And minus v1 plus 2v2 is equal to 0. So finally we get these two equations which are actually the same. So we can use any eigenvector such that v1 is equal to 2v2. So this whole family of eigenvectors, that is 2, 1, 4, 2, 6, 3 and so on, satisfies this equation. You can verify this by plugging in any of these eigenvectors with eigenvalues of 2 in this equation, av is equal to lambda v. Great. My dear students, following the same procedure, we can calculate the second eigenvector corresponding to the eigenvalue of minus 5, which finally comes out to be this 1 minus 3, 2 minus 6, 3 minus 9 and so on. And of course you can verify that by substituting that value over here. And finally in step 4, I have just normalized both the eigenvectors by dividing their elements with their respective L2 norms. So this was the vector 2, 1. So I have divided it with the L2 norm, and this was the vector 1 minus 3, and I have again divided it with the L2 norm. Great job done. Okay, so this was lengthier, doing it using the paper pencil. However, my dear students, while performing data science and machine learning tasks, we have to compute eigenvalues and eigenvectors of huge matrices, which is of course not possible using paper pencil. So for this we use this EIG method, method of the linear algebra module of the NumPy library, which returns a tuple containing the the eigenvalues that I'm receiving inside this variable lambda, and the eigenvector which I'm receiving in this matrix V. Let me execute it. Okay, so this 0.89 and 0.44, this first column, is the unit eigenvector corresponding to the eigenvalue of 2, this one. Similarly, this minus 0.32 and minus 0.94 roughly is the second unit eigenvector corresponding to the eigenvalue minus 5. And my dear students, you can compare it with these which we have calculated using the paper pencil. Great. Okay, so to have a crystal clear understanding, let us visually plot the first eigenvector before and after the transformation. I am using once again our old friendly helper function, this plot vector, to plot both the vectors. And let me execute this code. Oh, great. My dear friends, you can observe that the vector before transformation was 4, 2. This was the vector before transformation. And after matrix A was applied, it was scaled by a lambda value of 2 and has maintained its direction, being an eigenvector of matrix A. Great. And similarly, we can repeat this for the second eigenvector as well. Over here, we straight away run the code. Note that once we apply the transformation matrix A to this second eigenvector, its direction becomes exactly opposite, as its corresponding lambda value is negative. Moreover, it is scaled. Its length has increased 5 times. My dear students, I hope this is making sense to you all. Okay, now my dear students, now we have the transformation matrix A and its 2 eigenvectors and corresponding eigenvalues. So let us prove that from where we started, that is AV is equal to lambda V. So let me prove this, which means that if this V is the eigenvector of transformation matrix A, then multiplying this matrix A with this vector V is the same as multiplying the vector V with the corresponding eigenvalue. So let me execute this code. You see, this was the first eigenvector 0.8, 0.4. This is the first eigenvalue 2. And once we multiply AV and then we multiply lambda V, we get the same values. Hence, this is proof that AV is equal to lambda V. So for both the eigenvectors of matrix A, the left hand side is equal to the right hand side. And over here I am doing it for the second eigenvector as well. I hope this makes sense to you all. Okay, some more points to ponder related to eigenvalues and eigenvectors. Some properties. The first property is if you take the product of all the eigenvalues of a transformation matrix A, it is equal to the determinant of that matrix A. Okay, so this is a piece of code which is a proof of this concept. Let me straight away execute this. Note that this is a 3 by 3 matrix and this is the determinant of this matrix. You can calculate it using paper pencil as well. These are the eigenvalues, 3 eigenvalues of this matrix, and these are the product of the eigenvalues of the matrix A. So hence it is proved that given a matrix A, if you take the determinant of this matrix, this is 19.9, and if you find out all the eigenvalues of this matrix and you take their product, you get the same value. Great. Let me move on to the next property, and that says if you take the sum of all the eigenvalues of a transformation matrix A, it is equal to the trace of that matrix. And we all know that the trace of a matrix is the sum of the diagonal elements. And this is a piece of code that proves this concept. And let me execute it. So this is the matrix. These are the eigenvalues. Sum of the eigenvalues is, of course, minus 3. and the trace of the matrix is also -3. That is, sum of the diagonal elements, 1 plus -4 is -3. Great. Okay, and another point to keep in mind is that not all transformation matrices have real eigenvalues. For example, this is the matrix A that performs a 90-degree counterclockwise rotation. And in the code over here, we have used the EIG method to compute its eigenvalues and the eigenvectors. Let me execute the code. Okay. Note the eigenvectors of this rotation matrix are not real. Moreover, the eigenvalues are plus j and minus j, or plus I or minus I. The product of eigenvalues and the determinant of matrix is 1, and the sum of eigenvalues is the trace of the matrix, and that is 0. I hope this is making sense. The next important property that I want to talk about is that if you have a diagonal matrix, that is a matrix in which all the entries that are not in the main diagonal are 0, its eigenvectors will always be the basis vectors, and the diagonal elements are the eigenvalues. And let's see this example. Let me run the code simply. You see? Let me run this code. I hope this is making sense to you all. And let me run this code. So hence it is proved that if you have a diagonal matrix, its eigen values are actually the diagonal elements, -5, 2, -4. And its eigenvectors will always be the basis vectors. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are the 3 basis vectors for this 3D matrix. And for this we have a 1, 0 and 0, 1, a 2D matrix. These are the 2 basis vectors. Basis vector along the x-axis and along the y-axis, I hat, j hat. And the 2 diagonal values -1, 2, these are the 2 eigen values corresponding to these 2 eigenvectors. Great. So I think now we are well equipped to talk about the first decomposition technique, and that is Eigendecomposition. It will be a piece of cake with all this background. So let us eat this cake. My dear students, first thing is, given a matrix A, we can determine its eigenvalues and eigenvectors. Then we can write this matrix A as a product of 3 matrices as shown over here. This V is the matrix comprised of the eigenvectors of matrix A. This uppercase lambda is a diagonal matrix comprised of the eigenvalues of matrix A, as shown over here, with lambda 1 greater than lambda 2 is greater than lambda 3 and so on. And to visualize this, I have just written this equation in matrix shape for a 3 by 3 matrix. Once again, note this, this is a 3 by 3 matrix A, and we have decomposed it into 3 matrices. This is the first matrix V, whose 3 columns are the 3 eigenvectors. First eigenvector, second eigenvector, and third eigenvector. This second matrix is the diagonal matrix of containing the 3 eigenvalues. This lambda 1 correspond to this eigenvector. This lambda 2 correspond to the second eigenvector. This lambda 3 correspond to the third eigenvector. And finally, this is the third matrix, which is the inverse of this matrix V. Let us understand this with an example. Okay, given this 2 by 2 matrix A, let us decompose it using Eigendecomposition, and let's prove that the matrix A can be written as a product of the 3 matrices V, uppercase lambda, and this V inverse. Okay, so this is the first line, which is actually creating this matrix, 2 by 2 matrix, 4, -5, 2, -3. This second line is using the EIG method to calculate the eigenvalues and eigenvectors of matrix A. This is the third line where I am using the dig diagonal method of the NumPy, and that is to create our diagonal matrix of the eigenvalues lambdas. So note that this variable is having a capital L with a lambda. So this lambda is of course a vector, and this will be a diagonal matrix. And this line is actually calculating the inverse of this matrix V using the INV method of linear algebra module of NumPy. And over here in this last line over here, what I'm doing is I'm just multiplying the three matrices V, lambda and V inverse. Let me execute the code. So this was the matrix A, this was matrix V, this was matrix lambda containing the eigenvalues, this is the inverse of V, and once I have multiplied these three component matrices V, lambda and V inverse, I have got this matrix 4, minus 5, 2, minus 3, which is the same as matrix A. And this is what eigendecomposition is. Once again, given a matrix A, I have decomposed it into three matrices V, lambda and V inverse, and once I multiply these three matrices, I get the same matrix back. And this is what I have theoretically said over here. Okay, so before proceeding ahead, let me quickly tell you one of the very common use of eigendecomposition, and that is taking the power of a matrix. Suppose we want to take the power of this 2 by 2 matrix. I want to compute the power of A as 16. This is the code that will do this task. The operation requires you see 4 steps. Log base 2 16 is 4. So it requires log n operations. And you can imagine if n is very large, this operation is quite inefficient. Let me run it. So this is the result. A power 16. Great. Let me show you how eigendecomposition can help us to perform the power of a matrix more efficiently. Suppose that these are the 16 matrices that we want to multiply. A dot A dot A dot so on to 16 times. I can replace every matrix with their component matrices V, lambda, the uppercase lambda or bigger lambda, and V inverse. So we have the expression something like this. And since this V inverse V, once we multiply these two matrices, or once we multiply a matrix with its inverse, we get an identity matrix. So this expression can be reduced down to just three multiplications. That is V, this bigger lambda power 16, and V inverse. All the in between V inverse V matrices reduced to identity, and once we multiply identity with any matrix, we get that matrix. So we have this expression. And to compute the 16th power of this diagonal matrix, it is again a very simple operation, as most of its elements are 0, and we just have to take the power of the diagonal elements only. So now if you review this code, this will make sense. Let me execute this. Note the two eigenvalues are 2 and minus 1. Also note that the 16th power of the diagonal matrix uppercase lambda is 65536 over here, and over here we have 1. So 65536 and 1. And finally we have just multiplied the three matrices, and you got the same result. Let me show you the result over here and the result over here. So of course this is computationally far less expensive as compared to taking the 16 matrices and multiply them one by one. Okay, so my dear students, eigen decomposition can be made simpler if the matrix A is a symmetric matrix. In case if A is a symmetric matrix, you don't have to compute its inverse, which is of course an expensive operation. So for a symmetric matrix A, its eigen decomposition is Q uppercase lambda and Q transpose. And another point to keep in mind is for a symmetric matrix, the eigenvalues are real and the eigenvectors are perpendicular. And here is the sample code for this. Okay, so let me just execute it. You see this is a symmetric matrix A, and we have computed the eigenvalues as well as the eigenvectors. And I have taken the diagonal and I have taken the transpose. This is the key point. I have not taken the inverse this time. So I have decomposed this symmetric matrix into three matrices, Q and Q transpose and this uppercase lambda. So over here we don't have the inverse. So the proof is once we multiply all these matrices, Q, the lambda and Qt, we get the same matrix back, that is 2 1 1 2. Great job done. Okay, so we are done with eigen decomposition. Let's move on to the next decomposition technique, and that is known as singular value decomposition. My dear students, after having a clear understanding of eigen decomposition, let's now understand this SVD, which is a very commonly used decomposition technique in machine learning algorithms. I will not be wrong if I say that SVD is the most commonly used technique of linear algebra, having its application in computer science, machine learning, as well as in statistics. Well, the way eigen decomposition divides a matrix into three component matrices, SVD also divides the matrix into product of three matrices. However, unlike eigen decomposition, which is applicable to square matrices only, SVD works for rectangular matrices as well. Therefore, unlike eigen decomposition, all matrices can be decomposed using SVD. Which makes this technique more stable and more commonly used than the eigen decomposition. Well, before we compute the SVD of a matrix, let's first understand it at an abstract level. Suppose we have a matrix A having m rows and n columns, and we want to represent this matrix as a product of three matrices U, sigma, and V transpose. Well, this matrix U is a m by m orthogonal matrix whose columns are the unit eigenvectors of AA transpose, also called the left singular vectors. Similarly, this matrix V transpose over here is a n by n matrix, orthogonal matrix, whose rows are the unit eigenvectors of A transpose A, also called the right singular vectors. And this middle matrix sigma is a n by n diagonal matrix with singular values of matrix A along the main diagonal, and all the other values are 0. And remember, the singular values of A are actually the square roots of the positive eigenvalues of A transpose A or AA transpose. And of course, these need to be arranged in decreasing order such that this value is greater than or equal to this value, and this value is greater than or equal to this value, and so on. And let me reiterate this by taking this example now. Having 5 rows and 3 columns, a 5 by 3 matrix. And let me decompose it using SVD. Once you compute the unit eigenvectors of A transpose, it will be a 5 by 5 matrix U. However, we will be using its 3 columns only. When we compute the unit eigenvectors of A transpose A, it will be a 3 by 3 matrix V. And of course, we take its transpose so that we get the row vectors like this. Now this first column vector of U correspond to this first singular value sigma 1 and this first row vector of this matrix Vt. Similarly, this second column vector of U correspond to this second singular value sigma 2 and this second row vector of Vt, and this process goes on. Remember the relative importance of these column vectors of U and these row vectors of V transpose are given by the corresponding singular values in this diagonal matrix sigma. And of course, we know that sigma 1 will always be greater than or equal to sigma 2 and sigma 2 will always be greater than or equal to sigma 3 and so on. Okay, so let's see how we can calculate it. My dear students, you can perform SVD by calculating the eigenvectors of A transpose, which makes the matrix U, or by calculating the eigenvectors of A transpose A, which makes the matrix V, and can compute the singular values of A and arrange them in decreasing order to make the matrix sigma. Let me use the NumPy library and do this. So this is the matrix A, and over here I am using the SVD method of the linear algebra module of the NumPy library to perform the singular value decomposition of this matrix A, and of course it returns these 3 components. First is the U matrix containing eigenvectors of A transpose. This vector small s containing singular values of A, and this matrix Vt containing the transpose of the eigenvectors of A transpose A. Over here I am using the diagonal method of NumPy to convert this vector small s to this diagonal matrix capital S, which is mentioned sigma over here above. Okay, so note in the output, let me run this code so that you can map it onto the values. So this is the matrix A. This is a 5 by 3 matrix A. Note this matrix U, which is a 5 by 5 matrix. Note this matrix S, which is a diagonal matrix, a 3 by 3 matrix containing the singular values of matrix A along the diagonal. This is the largest value, 18.6, then we have 5.8, and then we have 2.8, and this matrix Vt, which is a 3 by 3 matrix. And if we want to generate the matrix A from these 3 matrices, we just need to multiply this U, then we have S and we have Vt. So what we have done over here, so since this U is a 5 by 5 matrix, and to multiply it with this S, which is a 3 by 3, I have to slice this matrix U. So I have taken over here all the rows and the first 3 columns only, and then I have multiplied it. So you see we have got the same matrix A. By difference, once again, this is just for the making this U, S and VT compatible to be multiplied. And to avoid this, we have a shortcut. If I pass to this SVD method this argument, full matrices is equal to false, this will output this U matrix as a 3 by 3 matrix, 5 by 3 matrix. Let me run this. So this is the same code, but over here we have a 5 by 3 matrix U, a 3 by 3 matrix S and a 3 by 3 matrix VT, and they can simply be multiplied like this. So my difference, once again, this piece of code and this piece of code are quite similar. The only difference is that by default the SVD method output the matrix U as a square matrix, but if you pass full matrices is equal to false, this argument to this SVD method, it will generate the matrix U as a 5 by 3 matrix so that it can easily be multiplied with S and VT. I hope this makes sense. Okay. My dear students, the way we have used the SVD method of NumPy, we can use the SVD method of linear algebra module of SciPy as well, which is quite similar to the NumPy SVD method. So let me execute it. So you see it also gives you the same matrix. So either you can use the SVD method of linear algebra module of NumPy to do the task, or you can use the SVD method of the linear algebra module of SciPy. And some people prefer the Scikit-learn library as well. So in Scikit-learn library, we have to import this randomized underscore SVD method. I have used randomized underscore SVD method this time and done the job. So this is again same. Do note the n components argument of this randomized SVD, which specifies the number of singular values and vectors to extract. We will talk about this when we will understand the image compression in the next session, inshallah. For the time being, just remember that we are going to use the NumPy method for the NumPy SVD method for the rest of this lecture. However, if you come across some code which is using this SciPy library or this Scikit-learn library, I hope this will not confuse you much. Okay, let me move ahead to the next session, and that is the application of SVD and Eigendecomposition. Well, my dear friends, I defined matrix decomposition in our previous section as the process of reducing a matrix to its constituent parts in order to make certain matrix calculations simpler. Now that we know the two most commonly used matrix decomposition techniques, let us see where we can apply them in the domain of machine learning, deep learning, and natural language processing. Well, in today's session, I will cover how we can use eigendecomposition and singular value decomposition in image compression, principal component analysis, and calculating the inverse of a non-square matrix using Moore-Penrose Pseudoinverse. Well, I will cover the rest in the machine learning module of this course, like Netflix movie recommendation system, Google PageRank algorithm, document clustering in natural language processing. These all algorithms use singular value decomposition behind the curtain. So let's move to image compression first. So let's start with applying this SVD on the concept of reducing the size of an image. Well, my dear friends, consider this a grayscale image of the digit 0 that is encoded using 64 pixels or values as an 8 by 8 matrix as shown over here. The value inside this matrix range from 0 representing a pure black color to 15 representing a pure white color. Suppose this pixel at the top right over here, this top right pixel is pure black and the corresponding value is 0. And similarly, in the image, note that at location row 1 and column 5, row 1 and 0, 1, 2, 3, 3, 4 and 5, this. And this is pure white. So this pixel is pure white, and over here we have a value of 15 over here. So this is how the image of 0 is represented as a matrix. An image of 0 in 64 pixels, 8 by 8, is represented as a matrix of values having 8 rows and 8 columns. Now the question is, instead of storing this image in 64 values, can we store it using less number of values without losing much of the information? And to do this, let us quickly brush up some concepts that we have already covered before in this session of linear algebra. First of all, consider this rank 1 matrix, a 4 by 4 rank 1 matrix having 16 values. And if you observe closely, you can note that this second row over here, this -1, -2, -3, -4, this second row can be obtained by multiplying the first row by -1. Similarly, this third row can be obtained by multiplying the first row by 2, and this fourth row can be obtained by multiplying the first row by 10. Great. So actually we do not need to store these 16 values. Rather, we can just decompose this 4 by 4 matrix into a column vector and a row vector of 4 values each. And when we multiply these two, we get the original matrix. So instead of storing 16 values, we have just used 8 values. My dear students, if you have a 1000 by 1000 rank 1 matrix, you need 1 million values, and you can decompose it into just 2 vectors of 1000 elements each. So a compression from 1 million values to just 2000 values, saving a lot of space. Okay, now see this matrix. This is a rank 4 matrix, a 4 by 4 rank 4 matrix. Can you think of just 2 vectors that can encode all this information of this matrix? Or can you think of decomposing this matrix into just 2 vectors, a column vector and a row vector of size 4 each, so that when we take their dot product we get this original matrix? Probably the answer will be a no, and the reason is that this is a rank 4 matrix having 4 linearly independent rows or columns, or in simple words, you cannot add and scale one row or column to make the other. So the singular value decomposition come for our rescue. See up the same rank 4 matrix over here. We can approximate this matrix as a sum of maybe 2 or 3 or 4 rank 1 matrices. And of course the sum of the 4 will exactly generate the same metric, and the sum of the 3 will be quite close enough. Let me move down and show you something like this. Okay. Consider this 4 by 4 matrix A. We apply SVD and decompose it into these 3 matrices. this matrix U containing the left singular column vectors, matrix VT containing the right singular row vectors, and this diagonal matrix sigma containing singular values sigma 1, sigma 2, sigma 3 and sigma 4, and of course sigma 1 is greater than or equal to sigma 2, which is greater than or equal to sigma 3, which is greater than or equal to sigma 4. And once we multiply or take the dot product of all these three matrices, this is how they get multiplied. So this U1 is multiplied by this sigma 1 and this V1. This U2 get multiplied by sigma 2 and this V2. This U3 get multiplied by sigma 3 and V3. And this U4 get multiplied by sigma 4 and V4. And this is how it is written over here. And let's see a practical example. Okay, so now consider this 4 by 4 matrix. You can decompose it into this matrix U, sigma, and Vt. And we all know the SVD method of NumPy or randomized SVD method of Scikit-learn that can do the job for us. Well, if you take the first singular value, that is 21.2, and multiply it with the first column vector of U, that is this one, and then the first vector of this Vt, so we get this. And then I have taken the second singular value, second column vector of U, second row vector of Vt, I get this, and similarly this and this. So if I get this singular value, this column vector and this row vector, and I multiply it, I get this matrix, this 4 by 4 matrix. And if you compare this matrix with this one, they are not quite similar. However, if I take this one and add them up, I get this. Now you see this is a bit close to the matrix A. If I take this one plus this one plus this one, I get this matrix, and this is quite much close to the matrix A. And if I add all these 4 matrices, I get exactly the same matrix A. So for a matrix of size m by n, if you decide to consider the first or highest k sigma values, that will be the compressed size of the resulting matrix. Okay, so the original size is m by n and the compressed size is this, where k is the number of sigma values I want to consider. If k is 3, so I will take just the sum of these 3. If k is 2, I will just take the sum of these 2. Okay, so before I move on to an actual example, let me show you this over here. Let me execute the code. So this is the matrix A. This is the same matrix, 3, 5, 5, 9, 1, 9, 3, 7, and so on. So this is the matrix. I have used the SVD method of linear algebra module of NumPy to compute the 3 component matrices U, S, and Vt. So this is U, this is S, and this is Vt. So we can always generate the original matrix A by multiplying all these 3 matrices. So let me show you this. So this is the same matrix A. I have multiplied all of these 3. Okay, so let's see what over here I am doing. This piece of code is generating the first component only. Fine. Note this line. This is the line that is of our interest. Let me describe this line to you. So I am taking the first singular value as 0, 0, and this U colon 0 means, this colon means that select all the rows, and after comma this 0 means select the first column only. So I'm multiplying all the rows but just the first column of U with this Vt, And over here I'm reshaping it to a matrix of 4 by 1. So what actually I am doing is I'm taking this column from U, this column, and then I am multiplying it with the first row vector of VT, taking the first row, all the columns, and reshaping it to 1, 4. That is, I am multiplying it with this minus 0.55, minus 0.52, and this. So once I multiply all of these, what I get is I get this matrix. Taking the first column of U, the lambda value, eigenvalue at 0, 0 location, and the first row vector. Once we multiply them, I get this RV1. So this is what this RV1 is. So this is the first component. So you can do it the long way like this, and of course you can use the randomized SVD method of the Scikit-learn and pass it n components is equal to 1. So I hope now this makes sense to you. What does this n component means? By n component, I just mean that take the first component. If I pass n component is equal to 2, that means take this component plus this component. If I take n component is equal to 3, that means take this plus 3. Okay, so I hope this makes sense. So this is the same matrix which we have over here, 2.51 and 6.19, the last value. 2.51 and 6.19, the last value. Great. So let me do RV1 plus RV2. I have used the same piece of code, and this time I have got the sum of the first two components. Note the contents of this matrix is the same as the content of this matrix. So I have used two components. N component is equal to 2. Let me use three components now. N components is equal to 3. Let me execute it. And let me take 4 components. And you see we have got the same matrix back. My dear students, please stop the video, move back to this image. You should have a very clear understanding how I am taking the different components of U, sigma, and VT and generating these matrices from using this NumPy piece of code. Great, so far so good. My dear students, for completeness, let me show you an example of compressing a real image as well. Over here I am using the imread method of the image module of Matplotlib library, which is reading a JPG image of myself with my students, I think. Yes, these all are my students sitting with me before their graduation. Anyway, so this is the imread image, which is actually reading a JPG image and returns a 3-dimensional NumPy array having 1786 columns, 2880 rows, and this 3 means that this is a 3-channel image. I have used the imshow method of the pie plot of Matplotlib to display it. Okay, so let me convert it to a grayscale image so that I don't have to deal with the complexity of the multiple color channels. So this is the grayscale version. What I have done is I have just used the NumPy mean method to calculate the mean, and over here I have used the color map to gray, otherwise it will show you in a pale yellowish color. Okay, so let's now decompose. Over here I am using the SVD method, and I am getting the 3 matrices U, S, and VT, and of course these will be huge matrices. It is taking a bit of time because okay, so we have U, we have S, the diagonal matrix, and we have the V transpose. And now let us compress. Let me compress. Okay, over here what I'm doing is I'm taking all the rows but only the first k columns of u, and over here I am taking the first k values along the diagonal, and over here I am taking the first k rows, and k is let's suppose 10 this time, and so that is a compressed image, and I am using that I am show method again to display that. Let me run it. So this is a compressed image, you see. You can hardly recognize the faces over here. So what? Let me make it 50. So k is equal to 50. Now they are recognizable, but not all that good. Let me take 100. K is equal to 100. So this is a reasonable value for this image compression. And let me take all the components by taking this as 1786, and this is the actual image, very clear. Let me move back to 100. I think that much compression will do the job. So with 100 singular vectors, the size of this compressed image is reduced to how much? Let me, well, this is reduced from roughly from 4.9 MB to just 0.44 MB, and assuming that each pixel value is stored in 1 byte. That is great. That is really great. Let me move ahead. Okay, my dear students, we are learning different applications of singular value decomposition. We have already seen how to do image compression using SVD, and now we are going to learn another very important and heavily used algorithm of machine learning called the principal component analysis. Well, if you're watching this video from the beginning, then it's okay, but if not, then I assume that you have a fair idea about the nitty-gritties of Eigendecomposition and singular value decomposition. Now, instead of straight away jumping onto the definition of PCA, that is principal component analysis, and the steps to follow to compute the principal components, let me first set the stage right by giving you an example of a housing dataset. Okay, my dear students, consider this a snapshot of a portion of a housing dataset having 7 input variables like city, size, covered area, number of bedrooms, trees nearby, number of bathrooms, schools nearby, and so on. And finally, over here we have the output variable price, which we'll like to predict using some supervised machine learning algorithm, maybe using linear regression. But right now we are not interested in linear regression part, rather just need to decide whether the price of a house really depends on all these input variables and features. My dear students, right now I have just shown 7 input features, but there can be tens or maybe hundreds of them in the dataset. And this is what we call the curse of dimensionality. My dear students, remember, increasing the number of features does not always improve accuracy. When a dataset does not have enough features, our machine learning model is likely to underfit. And whenever the dataset has too many features, it is likely to overfit. And this is what we call the curse of dimensionality. Now the question is how to solve it. And one very simple solution is simply chop off the column like this trees nearby column. If you think that this really does not impact the price of a house, that how many trees are there near that house, so you can simply chop off this column. But the problem with this solution is what if there are hundreds of columns, and what if we ourselves do not have any idea as to which all input features, this output variable price depends. So better is to use some dimensionality reduction technique like principal component analysis, linear discriminant analysis, generalized discriminant analysis, this low variance filter, high correlation filter, backward feature elimination, and so on. And today we are going to discuss the principal component analysis, which is the process of figuring out most important features called the principal components which have the most impact on the target variable. Well, by reducing the dimensionality, we achieve two targets. First is that we speed up the training and testing time of different machine learning algorithms. And the second is that by reducing the dimensionality of a dataset to 2 or maybe 3 dimensions, we can visualize our dataset using our naked eye. Okay, fine. My dear friends, before we discuss the different steps involved to do the PCA, let me first describe the process at a very abstract level. Consider once again a housing dataset having let's suppose these 5 input variables: size of house, number of bedrooms, number of bathrooms, schools around, and park around. If you closely observe these 5 features, you can think of dividing them or shrinking them into just 2 features over here. 3 features are related to the size of the house, number of bedrooms, and number of bathrooms. All these 3 input variables are related to the size feature. And these 2 input parameters or variables, that is the number of schools around the house and the number of parks around, they are related to the location feature. So we can divide these 5 features into just features. So this size feature covers the first 3 features related to size, and this location feature relates to the last 2 features, that is the location of the house. And this is what dimensionality reduction is. That is, we went from 5 columns to just 2 columns. This column size feature will have different values that might be weighted average of these 3 columns related to the size of the house. And this location feature might have different values that be the weighted average of these 2 columns: schools around and park around. Let's see this example now. Over here, let's see this scatter plot at the left. This shows just 2 columns: number of bedrooms and the size of the house. And let's suppose that we want to reduce these 2 dimensions to a single dimension: the number of bedrooms and the size of the house. So these are the 10 data points, 10 houses. And you see, as the number of bedrooms increases, the size of the house also increases. There is a positive correlation between the 2 variables. Now in this middle figure, you see the red line. This is the red line, which might seem to you a linear regression line, but it is not for that purpose. Rather, it is the projection line on which we are projecting all our data points. Now in this right figure over here, you see that I have projected all these points to this red line. I have just moved them onto this red line. Of course, the xy coordinates of our dataset has changed a little bit. However, it is now not 2-dimensional, rather it is 1-dimensional. So if I draw this line like this over here, you see it is just 1-dimensional, having the 10 data points representing the size feature of the house. Let's see this feature, this image as well. Over here we are taking a different projection line. I have taken the projection line like this now, and I have projected all these data points onto this line, which has come up over here. However, if you compare this line having the 10 data points and this line having the 10 data points, you will observe that this is conveying more information than this line at the bottom, because over here we have more variance as compared to this projection. Anyway, we have successfully reduced our dataset from 2-dimension, that is the number of bedrooms and the size of the house, as shown over here, to a 1-dimensional dataset having only the size feature. Great. So this makes sense. 2D dataset has been reduced to a 1D dataset. And this is the animation that shows different projection lines of this hypothetical 2D dataset. And of course, the best projection line is this one, which is covering maximum variation. Probably this is making roughly the angle of 45 degrees in this particular scenario. Okay, I think now we are ready to understand the math involved to carry out the principal component analysis. And my dear students, let's suppose that you have n-dimensional dataset and you want to reduce it to k dimensions only, with of course minimum loss of information, and that can be done by keeping maximum variance. Well, the process is normally divided into 5 steps. Let me straight away jump on to an example and describe all these 5 steps one by one on some real-time data. Fine. So this is the hypothetical dataset of 9 houses with 6 input features that are used to predict the price of the house. So these are the 6 features, and this is the output feature, price. I have used the read CSV method of Pandas library to read the CSV file and load the dataset into Pandas data frame. My dear students, since PCA is an unsupervised algorithm, so I don't need this price. So I've just taken just the initial column. So this is the size, covered area, bedrooms, trees nearby, bathrooms, and schools nearby. So these are the 6 columns or input features. So okay, now this is the first step, and the first step is that we need to normalize or standardize the data to avoid any biasness towards a specific feature, and this is done by subtracting every data value from the mean of that column and then by dividing it by the standard deviation of that column. And the code is shown over here. It's simple. I have just used the NumPy mean method and std method to calculate the mean and standard deviation of every column. Let me execute this. So this is the matrix N containing the normalized dataset. Note that all the variables are transformed to the same scale. Okay, now the step 2 is to actually compute the covariance matrix of this normalized dataset that is there inside this matrix N. And I assume that we all know that covariance is actually a statistical measure to see how the mean of 2 random variables move together. Or put it in simple words, the covariance means to identify the positive, negative, or zero relationship between the features of the dataset. Over here I've used the COV method to compute the covariance matrix. Note that I have passed the transpose of the matrix N by making the 6 columns as 6 rows to get a 6 by 6 covariance matrix. Great. So along the main diagonal, this 1.12, 1.13, 1.12 and so on, we have the variance of the features, and every other element in this symmetric matrix indicate the covariance of 2 different variables. I hope this covariance, you know what is covariance. If you do not know that, please watch the probability and statistics part of the math for data science that we covered in the last session. Anyway, fine. So this is the covariance matrix. Let's move on to the next step. Fine. In step 3, we perform eigendecomposition of this covariance matrix to get the eigenvectors and eigenvalues. I have used the EIG method, and I've passed the covariance matrix to this EIG method of linear algebra module of NumPy library for this task. Let me simply execute this code. So these are the 1, 2, 3, 4, 5, 6 eigenvectors, and these are the corresponding 6 eigenvalues. So this is a 6 by 6 matrix because we had 6 features in our dataset, and these 6 columns are actually the 6 eigenvectors. Once again, this is the first eigenvector, this is the second eigenvector, and these are also called the principal components. So we have 6 principal components. This first column over here has a corresponding eigenvalue of 2.87. So it holds the maximum possible information and is called PC1. Then this fourth, 1, 2, 3, 4. This fourth column is PC2, principal component 2, because it corresponds to the eigenvalue of 1.46, and similarly this 1.29. This column is having is PC3 because it is having the third highest eigenvalue. I hope this makes sense. Okay, so step 4, we simply select k eigenvectors corresponding to k highest eigenvalue and create the feature matrix. And let's suppose that we want to decrease the dimension of our dataset to 2 from 6. So let me select this first 2.87, this column. I need to select this column, and the next highest is this 1.49. So I need to select this fourth column, 1, 2, 3, 4, this one. So I have selected these 2 columns over here. So these are the 2 columns that I have selected. The first principal component, and this is the second principal component. So this is the first and this is the second. Great. Let's move to step 5. This is the last step to create the final dataset having 2 dimensions only by multiplying the data matrix n with the feature matrix. So this is size of the initial matrix, this is the size of the feature matrix, and of course we can multiply them, they are compatible. So this is the projected data. Let me produce the pandas data frame from these 2 principal components. I have just called the data frame method of PD and passed it this NumPy. So I have it over here, and finally of course I can concatenate this data frame with the price column that I have done over here. So this is your data frame having a dimensionality of 2. So just 2 components on which the price of a house depends. So my dear students, this is a housing dataset reduced from 6 dimensions or 6 input features to just 2 principal components. We can now use this dataset instead and carry out or execute the regression algorithm, which we will inshallah do in the machine learning module of this course. My dear students, in real life you don't actually follow all these steps to perform PCA. Rather, there are libraries that makes our life quite comfortable. Let us move on to our next example where we will use a Scikit-learn library to do a dimensionality reduction on another dataset. Okay, so this is the second example of principal component analysis. In previous example, we use a housing dataset and we reduce the dimensionality from 6 input features to just 2 features before applying linear regression on it. Moreover, in the previous example, we used a step-by-step approach and practically understood all the math involved behind PCA. In this example, we will instead use the Scikit-learn library methods to perform PCA. That will hide all the mathematical and statistical details and make our life easier. Well, the dataset I am using for this example is a classification example. Anyway, given any of these images, the system has to classify the image into one of the 10 classes. That is be it the image of digit 0, 1, 2, 3, 4, and so on to 9. For simplicity, let me assume that every image of a digit is encoded as a matrix of size 8 by 8, having values representing the pixel intensities ranging from 0 to 16, I think, over here, where a value of 0 represents the black color and a value of 16 represents the white color. Please pause the video, spend some time to match different pixel inside these 9 images and the corresponding pixel intensities in the matrices shown with these images. And let me move on to a link over here, that is the link of the Scikit-learn library. My dear students, Scikit-learn is a machine learning library for Python programming language and features various regression, classification, as well as clustering algorithms. And inshallah, we will explore it in detail in our machine learning algorithm. For the time being, I just want to use one of the toy datasets. There are many toy datasets over here. For example, this Boston dataset, it is getting obsolete, I think, deprecated. However, it deals with the houses. We have the iris dataset and the digits dataset that are used for classification. Let me scroll down and see the characteristics of digits dataset. Okay, so here it is. Well, there are 1797 records. Each record or row has 64 features or attributes. Each row contains 64 pixel intensity values actually in the range of 0 to 16. And this dataset contains images of handwritten digits, 10 classes, where each class refers to a digit. Please do go through with this. Let me fall back to the Jupyter Notebook slide. Okay, so step 1 is to load the data. And I'm using the load underscore digits method of the datasets module of Scikit-learn library. So this method returns a dictionary object that I am keeping inside this variable named digits underscore dict. Let me execute this. Over here, if you know what our dictionary is, the keys is a method of a dictionary object, and it tells us that there are different keys, and all these keys will of course have their corresponding values. There is a key data, there is a key target, and there is a key frame, and so on, and they will be having their corresponding values. Let us first check out the value of the key data. Let me run this. You see, this is the data, and its shape is 1797 rows and 64 columns. So the data is actually a 2D NumPy array or matrix having 1797 rows and 64 columns, and most probably it contains the pixel intensities of the different digits. Let me show you what is there inside the target key. And the shape of it is 1797. So it is just a vector containing 1797 output values, 0, 1, 2, and so on to 9. So the target is actually a 1D NumPy array having 1797 values, which is actually the output value for every record, that is a digit, starting from 0 to 9. And let me confirm this by checking out the 100th row. So this is the 100th row, 64 pixel intensities of the 100th record. And let me check out the target. So that means this is the digit 4. Let me check out the data at the 10th row. Can you tell me which digit this is? Well, this is digit 0. Great, great. And of course, you can do it something like this as well. You can reshape the data at row 100 into a 8 by 8 matrix. And of course, you can use the IMShow method of pyplot module of matplotlib to check out what this digit is. So this is digit 0. At 100 we have digit 0. Or let me check it out from here. No, this is 4. Okay, so this is 4. Yes, it makes 4. Great. Anyway, so for better display of data, let me put this data inside a pandas data frame and see that. So this is a pandas data frame. You can see we have 1797 rows and we have 64 columns. Each column has a corresponding pixel value. This row pertains to one digit, this row pertains to another digit, this row pertains to another digit, and so on. And let me show you the data frame for the output as well. So this is the output, and let me concatenate both of these to have a complete data frame. So 1797 rows, and now we have 65 columns. So this is the first row, second row, third row, and we have the output column this time. So this row is containing the pixel intensities for digit 0, for digit 1, for digit 2, and so on. I hope this is making sense to you all. Remember, my dear friends, before you start working on some project, you should have a fair idea about the data set on which you are going to work. Anyway, so finally, I am doing what? I am taking all this data inside a NumPy array or a matrix named A. So this is the matrix A having 1797 rows and 64 columns. Great. And let's see that what we want to do is we want to compute the principal component analysis or the principal components. So the second step is the standardization of data. And this time what we are going to do is we are going to use Scikit-learn for this. So what I'm going to use is I'm going to use the standard scalar class which is there in the pre-processing module of Scikit-learn or sklearn library. And this standard scalar method returns a scalar object, and then I'm calling the fit method on this object with the input data, that is A, which will calculate the mean and standard deviation for all the 64 columns or feature. Finally, we call the transform method over here, and this method of scalar object returns the normalized or standardized data having 1797 rows and of course 64 columns. So this is the standardized data. So instead of doing it the long way, I am just calling the standard scalar. I'm just creating the object of standard scalar method, and then I'm calling the fit and the transform method. Instead of calling the fit and the transform method separately, you can just call this method fit underscore transform. That will do the same job. Let me move on to the third step. Now we are ready to apply PCA on the normalized dataset. For this, we need to create an object of PCA. So over here, I'm calling the PCA method. To this PCA method of the decomposition module of sklearn, you can pass nothing, as I have done over here, which is the default. It will keep all the 64 principal components in this object. And if I pass n underscore components is equal to 20, it will keep that much number of principal component in this PCA object. And I can always keep a value from 0 to 1. For example, over here I am passing 0.9. Then the algorithm will select the number of components while preserving 90% of the variability in the data. So if you don't want to mention the number of components you want to keep, you just want to have 90% variability or 95% variability. So you just pass a value between 0 and 1, showing the percentage or the amount of variability you want to keep in this object. Okay, after that you need to call the fit and the transform method on PCA, or you can call the fit underscore transform method instead. Let me run it. Remember, I have kept 0.9 over here. So this is the output of the code. So there are 31 principal components. So that means in this matrix we have 31 columns. That will cover almost 90% of the variation. Great. Let me run this. So great. This can be confirmed by checking out the value of explained underscore variance underscore ratio underscore attribute of the PC object. And see, this output shows that the PC1 is covering almost 12.03% of information. PC2 is covering 9.5% of the information. PC3 is covering 8.44% of the information, and so on. And let me do it like this. And over here I'm just taking the cumulative sum. So the first component is having 12% information. The first 10 components are covering 58% information. The first 20 are covering 79% information, and almost 31 principal components are covering 90% of the information. So I hope this all is making sense to you. So we have just kept 31 principal components. Instead of 64 columns, we have reduced to just 31 columns, and we are covering 90% of the information of the dataset. Okay, for completeness, let us create a data frame having all these 31 columns. Great. And let me concatenate it with the output column as well. Now we have, remember, we have 1797 rows and 32 columns. The first 31 columns are actually the principal components, and the last column is the output, that is the digit. So we have reduced the dimensionality from 64 to just 31 columns. You can now run your classification machine learning algorithm on this reduced dimensionality dataset. It will give you much better performance, I'm sure. Okay, my dear students, in the previous two examples, we applied PCA on two datasets and reduced the dimensionality. First dataset was the housing dataset, on which we wanted to apply some regression algorithm. Second dataset was the digits dataset, on which we wanted to apply some classification algorithm. The objective of both previous examples was to reduce the training and testing time of the machine learning algorithm by reducing the dimensionality. And this example 3, I will try to describe another use of PCA, and that is data visualization. I mean reducing the dataset to 2 dimensions or maybe 3 dimensions, so that we can plot the data in 2D space for better visualization with naked eye. The goal in such problems is to discover the first 2 principal components, or maybe 3, which might help us in clustering our dataset as shown over here. Okay, once again, for this example, let me use the famous Iris dataset that was introduced by British statisticians Sir R.A. Fisher in his paper back in 1936. Before I load this dataset using the load iris method of datasets module of Scikit-learn library, let me quickly describe this flower to you. As shown in the figure, these are the 3 species of iris flower: Iris setosa, Iris versicolor, and Iris virginica. Further note that the 2 types of leaves that almost every flower has are the sepal and the petal. This sepal is the outer part of a flower that provides protection to the flower during its bud stage, and this petal are the inner leaves that surround the reproductive unit of a flower. Okay, so do visit this page over here, and the toy datasets. So this is the data regarding the iris dataset. Well, there are 150 records or rows in this dataset containing 4 attributes of a flower. The first 50 contains sepal length, sepal width, and petal length, petal width of the iris setosa. Next 50 rows contains the same observation for 50 versicolor, and last 50 rows have the same information for 50 virginica flowers. Let me move on to this Jupyter notebook and load this dataset. So we have got the dictionary as usual, as we have seen in the previous example as well. So we have these different keys of the dictionary, 7 keys. All these keys will of course have corresponding values. Let me show you the value corresponding to data. This is a 2D NumPy array or matrix having of course 150 rows, and each row contains 4 measurements of an instance of iris flower. The sepal length, sepal width, petal length and petal width, all in centimeters. So 150 rows and 4 columns. So this is the shape of the data. Let's check out the target as well. The shape of the target is 150. So this is a 1D NumPy array having 150 values. The initial 50 zeros means iris setosa. The next 50 ones means iris versicolor, and the last 50 twos means iris virginica. Let me show you the target names. So these are the 3 flowers, setosa, versicolor and virginica, and their feature names as well. The 4 columns, sepal length, sepal width, petal length and petal width. My dear students, if you want to read the details of this dataset, check out the description key of the dictionary object iris dict. I think now we have a fair idea about the iris dataset. Let's fall back to the actual problem, and that is dimensionality reduction. Okay, so let me load this data inside NumPy array A. And my dear students, since all the columns of our dataset contains measurements in the same scale, so we do not really need to standardize or normalize our data for this example as we have done in the previous examples. Let me move on to the step 3. As in the previous example, here as well we are creating the object PCA, a PCA class which is there in the decomposition module of Scikit-learn library. Let's suppose this time we want to plot the data for visualization, so we need to reduce the dimensions of our dataset from 4 to just 2. So I have passed n components is equal to 2 this time, and then I'm calling this fit underscore transform method of this PCA object. Let me just simply execute this code. So these are the 2 principal components, and you can see the first principal component is capturing 92% of the information, and this second principal component is capturing just 5% of the information. So cumulatively, these 2 principal components together are holding almost 98% of information of our entire iris dataset. Let's move on to the step 4. My dear students, since we have successfully reduced the dimension of our dataset from 4 to 2, we can plot this data using the scatter plot method. Great. So we have used the scatter method of the pyplot module of matplotlib library. Note I have just passed the first component as x argument and the second component as the y argument. So these are the 150 different flowers. Let me pass the color argument for better visualization. So I am passing just the color argument, the target. We have 3 targets, great. So these are the 150 dots which represent the 150 flowers, and you can observe that there is a clear structure here. The 3 groups or clusters of flowers are visible to us. So that means the new dataset having the reduced dimensionality still identify the hidden structure of the dataset. So far so good, great. Well, my dear students, I have tried my best to cover up all the nitty-gritties involved in computing and understanding of the principal component analysis, and that is dimensionality reduction technique using 3 datasets housing digits and iris flower. I hope you will be able to extend this knowledge and learn new and latest techniques of dimensionality reduction at your own. And let me move on to the third and the last application area of SVD, and that is pseudo-inverse. My dear students, so far we have covered 2 application areas of singular value decomposition. We have seen how to compress the size of an image using SVD. Then we discussed in detail the famous machine learning algorithm principal component analysis, which also uses singular value decomposition in order to perform dimensionality reduction. Now we are going to learn the third application of SVD, and that is solving a system of linear equations using Moore-Penrose Pseudoinverse and least square linear regression. We have discussed in detail about the topic of solving system of linear equations in our previous session of linear algebra. But before understanding the pseudo-inverse, let me have a quick recap. Well, my dear students, we all know that a system of linear equations can be consistent, having a unique solution or maybe having infinite solution. And a system of linear equations can be inconsistent, having no solution at all. And these are some of the examples of 2 variables and 2 equations. The equations as well as their graphical representation are shown. And in the previous session, we also discussed in detail regarding the overdetermined as well as the underdetermined system of linear equations. An overdetermined system of linear equation is the one having more number of equations than the number of unknowns. And this is a very common scenario that we come across in machine learning and data science. Okay, let's consider this system of linear equations having 4 equations but just 2 unknowns, x1 and x2. And these 4 equations can be written in matrix form as shown over here. Now to solve for the vector of unknown, that is this x, we need to compute the inverse of this matrix of coefficient as shown over here. And since this time this A is not a square matrix, therefore we cannot compute its simple inverse. However, singular value decomposition allows us to approximately invert a rectangular matrix A and compute its inverse, that is known as the pseudo inverse, that I have represented with a dagger over here. So this is the pseudo inverse symbol. And then of course we can find the best fit for x. Okay, my dear friends, if A is a small rectangular matrix, you can use this option of pseudo inverse. Ax is equal to b, this is the equation. Multiplying both sides of this equation with A transpose, we get a square matrix, that is A transpose A, whose inverse can be calculated of course, provided if it is not singular, having a determinant of 0. So if all these conditions are met, the pseudo inverse of a non-square matrix is given by this equation, this last equation, A transpose A, the inverse of this multiplied by A transpose. Option 2 uses SVD and is more stable as it works for singular matrices as well as having a determinant of 0. Let me quickly describe this over here, the math behind it. The pseudo inverse of a matrix A. So you have this equation Ax is equal to b, and this is the SVD, singular value decomposition of this matrix A. You write down U as Vt instead of A. And since U is orthogonal, and we know that when an orthogonal matrix is multiplied by its transpose, it will return an identity matrix. So we reduce it to somewhat over here. And since S, as we all know, that is a diagonal matrix, therefore S plus is equal to I. So we reduce back to this. And of course, this S plus is the reciprocal of all the non-zero elements and taking its transpose. So anyway, once again, we have on the left side just this V transpose. So once again, V is orthogonal, and we multiply it with V, and we get identity matrix. And so finally, this equation is reduced to X is equal to V S inverse U transpose and B. So this is what the pseudo inverse is. That is, A dagger is equal to the product of three matrices V, S plus and U transpose. I hope this math is a bit clear to you. Let me do it practically. Consider this non-square matrix. Let's calculate its pseudo inverse. My dear students, you cannot calculate the pseudo inverse of this because it has it will give you an error, because you cannot calculate the determinant of a non-square matrix. However, we have the three options for this. The first option is using the SVD. That is, we decompose the A matrix. Rather, we take this pseudo inverse V, S plus and UT. Here is the code that do the job. We use the SVD method of linear algebra module of NumPy to get U, S and Vt. I take the transpose of Vt to get V. So I have this first component. And to get the second component, that is S plus, which is a diagonal matrix with reciprocals of all non-zero elements. I have done it like this. And then finally I have multiplied all the three matrices. So this is a pseudo inverse. If this looks tricky to you, and since we can use this method as well, A transpose A, so this will also give us almost the same output. And if this is also tricky to you, you can simply use the PINV pseudo inverse method of the linear algebra module of NumPy to compute the pseudo inverse of this matrix A. So this is just for making you understand the math, and actually whenever you are requiring a pseudo inverse in your machine learning code, you use the PINV method. Great. Right, let me take another example for completeness. My dear students, although this is a square matrix, even then you cannot compute its inverse, and this is because it has a determinant of 0. So that means this is a square matrix but singular, so its inverse cannot be computed. However, we can use SVD as we have done above to compute its inverse. We can use we cannot use this as well, because this option will not work this time, because we have this line generating an error and saying that this is a singular matrix. Let me comment this. However, this PINV method will work all the time, so it will generate the pseudo inverse of this matrix A. Great. So now we know how to compute the pseudo inverse. Let's solve an overdetermined system of linear equation. Okay, suppose these are the 7 observations. My dear students, we have touched upon this example in our previous session as well, so I will quickly brush up the things. So these are the 7 observations that a teacher has taken. This first value represents the number of hours that a student had studied daily in the entire semester. And this second value represents the GPA that the student has secured. Let me just plot the 7 observations using a scatter plot. So this is a scatter plot. So GPA and the study hours, 1, 2, 3, 4, 5, 6 and 7 observations. My dear students, we all know the line equation y is equal to c plus mx, or y is equal to beta naught plus beta 1 x, where beta naught is the y-intercept, beta 1 is the slope, and these are the 7 equations corresponding to the 7 data points. So this is the first data point, 1 comma 1.4. So beta 0 plus beta 1 is equal to 1.4. My dear students, I have taken the y-intercept as 1 for all the values. Okay. So I have written the 7 equation in matrix form as shown over here. This is the matrix A, this is the matrix X, and this is the matrix or vector B. So the y-intercept is 1. So A is a 7 by 2 matrix of known coefficients. X is a 2 by 1 vector of unknowns. And over here B is a 7 by 1 vector of a known output. And here is the code that is going to create this matrix of 1. And here is the code that is create a matrix of the study hours. And over here I've used the H-stack method to generate the matrix A. So this is the matrix A, column 1 and 1, 2, 3, 4, 5, 6, 7, the study hours. So I have used the H-stack method of NumPy to horizontally concatenate these two columns. And this is B, that is the vector GPA. Great. So let's solve the system of linear equation now, and for that we need to calculate the pseudo-inverse of A. We need to compute the pseudo-inverse of A because this is not a square matrix. We need to compute pseudo-inverse. The regular inverse does not exist, and this is the way to compute the pseudo-inverse. This is one way, this is the other way, and this is the third way. So you know all the values are same no matter which technique you use. So while doing your machine learning task, you use this P inverse method. And over here I am actually multiplying the this matrix A dagger with the B to get the result. So this is the y-intercept, which is 0.9, and this is the slope, which is 0.46. So now since I have the slope as well as the y-intercept, I have the equation. That is 0.9 plus 0.464 into the study hours. Great. I hope that this all is making sense to you. Let me over here use the plot method and draw the regression line. So this is the best fit regression line over here. Great. And of course you can predict now. You just give me the study hours and its corresponding GPA can be calculated from this best fit line. So if a student is studying, let's suppose 2.5 hours daily, so he will get roughly 2.1 GPA. Great, great. Fine, and of course we discussed in detail as how to calculate the R-squared error that tell us how well the regression line actually fits the data. Let me just execute this code. And great. So this tells us that almost 96% of the variation in GPA can be explained by the number of hours studied. Great. Well, my dear students, that is all for today's session. We will inshallah continue our journey to learn some new topics of this course titled Tools and Techniques for Data Science. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.